Hello everyone, once again. Do you all see my screen and can you hear me well?
Yeah,
Awesome. Yeah, so welcome to the next lecture, right? Today we're gonna talk about time varying magnetic fields, eddy currents, and transformers. And your next lab work will be about simulating uh, electric transformer. Okay. Uh, So yeah, as usual, let us start from brief recap what we've discussed last time, which will make the basis for our today's lecture. Right. So as usual, we're starting from four Maxwell equations. I believe after these lectures you will remember them very well. Right. Again, so the first one is the Gauss law, which basically describes the intensity of electric field uh, through the source of the field, right? So the divergence of electric field in any point in space is given by the charge density, electric charge density in the same location, the same point. Uh, Next one is the Gauss law, which is a simple for the magnetism, right? Which is a simple statement that says we have no magnetic charges in nature. Okay, so people still work on searching for magnetic charges, so-called monopoles. There is some there are some theories of electromagnetism that say that probably they can exist, but they're so rare and weak. So if we ever like find them, observe them, we will have to modify these Maxwell equations. But so far, no magnetic charges have been observed in in any of those experiments. Right. More interesting law, which is Faraday law of induction. Today we're gonna use this one kind of a lot, which basically states that if I have any magnetic field which is changing in time, varying in time, this magnetic field creates the curl of electric field. Curl of electric field. And a similar equation for the magnetic field, right? So the change of electric field in time, as well as the current of electric charges, electrons, for example, creates the curl of magnetic field. This is basically that magnetic field which is always exists around any currents, like if you have any wire around you, you can be sure that that wire is surrounded by magnetic field. If current oscillates in time, let's say with frequency 60 gigahertz, that magnetic field also oscillates in time. And we will be talking about this second term here a little bit more. It's called Maxwell addition. All right, so yeah, last time we discussed mainly the the equations of magnetostatics, which means that if we have a current, we assume this current to be non-time changing, not time varying. Similarly, magnetic field assumed to be not time dependent, so this Faraday's law gets this simple form of curl electric field equal to zero, curl of magnetic field simply equal to its current. And we also introduced the concept of vectoral potential, vector potential A. We discussed how the magnetization is formed. Okay, so any magnetization, any magnetic field is attributed to a current. And in any material, we can always find some simple fundamental currents. Okay, this can be any kind of orbitals in atoms where electrons move around, spin around, or orbit around their nuclei. This is a element of single element of a current. Also, any type of spin, which is self kind of intrinsic rotation of electrons or nuclei, also generates magnetic field. So any current generates magnetic field. And if you have a system of such loop, current loops, and put the system in an external magnetic field, these magnetic dipoles will orient either along magnetic field or in the opposite direction to the opposite of magnetic field. And this is what causes the magnetic permeability, magnetization. And this is why we need to use two fields, B and H field. This is why we distinguish them. We discussed different materials in terms of magnetization. They can be diamagnetic, where magnetic dipoles orient in opposite direction to the external magnetic field. In this case, this object can repulse from magnetic field, leading to such a nice experiment result of a diamagnetic levitation, which is very weak effect. Another material is a paramagnetic, where the dipoles are induced along the magnetic field. So this medium, this material kind of is attracted to the magnetic field. And one example is shown here. This is the liquid oxygen. Okay, we discussed that in contrast to liquid nitrogen or just nitrogen, oxygen is attracted to the area of strong magnetic field. And this effect is significantly amplified in materials so-called as ferromagnetic materials, which have all magnetic dipoles oriented in the same direction, forming extremely large magnetic response and magnetic field. So in this case, any ferromagnetic material will be very strongly attracted to the field of large, to the area of large magnetic field, like shown here, for example. This is kind of a demonstration why we need to follow these safety procedures in terms of when we work with strong magnetic fields, like in MRIs. We also discussed the concept of electromotive force. Even though electromotive force requires the change of magnetic field in time, we consider it a wire which moves in the orthogonal magnetic field. This action leads to this Lorentz force, which acts on every single electron in this wire, leading to depletion of dividing the charges plus and minus charge. And this dividing of these two charges leads to the formation of electromotive force. We also said that it's not practical just to move the wire in magnetic field. We rather make it like a loop, coil, and then rotate this loop in a magnetic field, in a DC magnetic field. And this is how any generator works, essentially. Anytime magnetic field changes in a coil, in a wire, leads to formation of a electromotive force, this voltage, this potential that creates the current in the opposite direction, trying to compensate for the change of the magnetic field that caused this effect. Okay, so this is what we call inductance and induction, and this effect is described by inductance, denoted by L, right? And the definition of inductance, it's a parameter that describes any coil, and it stands like a parameter in this formula for the magnetic flux through the coil with a current I. Right, so yeah, any change of magnetic field creates electromotive force. We discussed two types of inductance, self-inductance and mutual inductance. This one I'm skipping because this is the part of your lab work, right? Again, you're supposed to simulate a coil and compare the result with the result from this formula. Mutual inductance is just the fact that if you have two coupled coils and changing of current in time in the coil 1 creates alternating magnetic field, which causes the change of the flux of magnetic field through the second coil, which leads to the creation of electromotive force in the second coil, right? And vice versa. So this effect is symmetric. And we say that it's used, for example, in electric transformers, and we're gonna discuss them today in more details. So let us start talking about, well, continue talking about time varying magnetic fields. When magnetic fields vary with time, they induce electric fields and currents in conductive materials. This is the first effect associated with changing magnetic field in time, the generation of electromotive force. Again, how we discuss this, describe, we starting from Faraday law of inductance. Here we assume that this right hand side is not zero, but acquires some values. So this is the rate of change of magnetic field in time. Notice this minus sign, right? So it just denotes the direction of the curl of electric field in response to the change of magnetic field. Yeah, so the Faraday law describes how time varying magnetic field induces an electromotive force. Let us integrate this equation over some arbitrary area shown here by this area, shaded area S. this equation is about electric field, magnetic field, right? So we're supposed to have in this space, we have electric field, magnetic field, and they both depend on time. So when we integrate the left-hand side, is the result is written here, right? So it's an integral over this surface over every single element of the surface dA. And by the Gauss law, or sorry, by the Stokes theorem, we can rewrite this integral as a circulation integral of this vector E over the closed path C, which basically surrounds the this area S, right? So this is how we rewrite the left hand side of this equation of the Faraday law, and the right hand side, which is the integral of the partial time derivative of B. We can exchange the time derivative and the integral, because they work with different variables, right? The integral runs over the coordinates, and the time derivative acts on the time variable. So we can exchange them, and as a result, this equation is rewritten in this integral, in this integral form. In this equation, we can recognize the equation, the value of the total magnetic flux, right? This integral of B vector over the surface area, right? So we substitute this formula here, and on the left-hand side, we then conclude that this left-hand side is nothing but electromotive force, right? So yeah, this is the equation for transformational electromotive force. And yeah, in this equation, in this definition of electromotive force, this minus here is nothing but the Lenz's law, right? Which basically indicates that this action, this induced electromotive force, always is induced the way to reduce the effect of change of magnetic field, to compensate that effect, compensate the effect of change of magnetic field. In this example, we assume that our wire, our coil, our loop is seated in the area of changing magnetic field, but the loop itself doesn't move. Okay, so the contour doesn't move. But another situation is possible when this loop, this coil, can move in a static magnetic field. In that case, the magnetic flux will be also changing, and let us discuss this effect in more detail. So I again refer to this simple experiment of wire moving in the orthogonal magnetic field. Every single electron experiences the action of the Lorentz force given by this formula, which results in the splitting of positive and negative charges. Okay, and if I, for example, accelerating this wire or increasing the magnetic field, this process will continue until the steady state when the Lorentz force acting on all electrons, all charges, will compensate for the electric field that is created by these divided positive and negative charges. Okay, so in the steady state, for every single electron, we will get this simple equation, basically the zero net force for every single electron. So from this equation, we come to this one. So the electric field induced in the wire will be given by this simple equation. And again, recalling the definition for the electromotive force, which is the integral. In this case, this integral will run over this wire of electric field times the element of the path. We'll get this integral for this particular case, and the result of this integration, since the velocity is constant, magnetic field is constant, so everything is constant. So, and the integral from 0 to L is just the length of the wire. We coming to this, I guess, known formula even from high school, right? So the electromotive force induced in a wire is proportional to the velocity, to the magnetic field, and the length of the wire, which means that if you need to increase this voltage, this EMF, you need to increase the speed of motion of this wire. If it's generator, you need to increase the angular velocity of this anchor rotation, right? Or you need to increase the magnetic field, which is technologically challenging for different reasons. So you cannot increase magnetic field very much. In contrast to electric field, by the way, we can discuss that another time for like why this is the reason. Simply speaking, when you have a system with strong magnetic field, this system tries to deform itself, kind of spread. And this process is described by so-called magnetic field pressure, which is proportional to the magnetic field squared. And when this magnetic field pressure exceeds the rigidity, right, of some of these ferromagnetic materials, rigidity, then system just breaks in parts, breaks down by the presence of this magnetic field. So yeah, so you cannot increase magnetic field like to up to very high intensities. And the length, of course, you can increase the length of the wire by just making a lot of windings, right? So potentially you can increase this electromotive force very much, by a very large factor. And of course, if in your space you have magnetic field and electric field, and in particular in any system with time oscillating magnetic field, you always have electric field there. So in general case, the electromotive force will be given by both factors, from electric field and from magnetic field. All right, do you have any questions? People still coming. All right. So one effect we just discussed that comes from time varying magnetic fields is the induction of electromotive force. Another effect is so-called or associated with displacement currents and Maxwell addition. So the story here is as follows. So initially, scientists use this equation, which is called Ampere's law, Ampere's equation, that well describes the magnetic field around currents, around wires with steady DC currents. Okay, and at the same time, we know that the charge, electric charge, must be conserved. By the way, if you don't know, this charge conservation law proposed by Benjamin Franklin, founding father Benjamin Franklin. It's a nice, interesting point. So we have this equation for the charge conservation law, which basically states that if some charges move out from some local area, which is described by this left-hand part, moving, right? The current means something, some charge moves out or moves in. It leads to the change of the charge density, which is described by this time derivative of charge density function. Yeah, so pretty simple. For example, if you have two bodies, one is charged by 10 coulomb, and another one is neutral, you can connect them. Of course, some charge will move from the charged body to the neutral body, and as a result, you will reach this equilibrium, right? But the total charge in the system will be conserved. Initially, it was plus 10 coulomb. Finally, it will be plus 10 coulomb. So the charge must be conserved. Even though some charge can move from one area to another area, trying to reach this electrostatic equilibrium. However, if you take the divergence of the Ampere's law, okay, Ampere's law, the divergence of curl of any vector is equal to 0. So you will get the result that divergence of current is equal to 0. So these two equations contradict, they don't agree. Okay, and the first person who noticed that this was Maxwell. And in order to fix this Ampere's law and to make it consistent with the charge conservation law, Maxwell introduced this term, which is called displacement current. Displacement current. And so the total Maxwell equation, just like we saw already, discussed several times, this one, corrected Ampere's law with the presence of this Maxwell addition. If you take the divergence of this corrected Ampere's law, you will see that it agrees with the charge conservation law. At the same time, this new addition to the equations leads to very interesting phenomena that lie in the heart of all modern communication and other technologies. Right, so let us consider a system without currents. Okay, so it can be free space. So I take this Ampere's law and just cross out the term with the current. So, and then I can take, for example, the curl of this resulting equation. Why not? Right, so taking the curl leads to this new equation. This curl of curl can be rewritten as the gradient of the divergence minus divergence of the gradient, right? And taking into account that the divergence of magnetic field is always zero, and also taking into account this second law of the Maxwell equation for the curl of electric field, right, leads to this equation for the, which is called wave equation, right? So this is particularly wave equation for the magnetic field, which connects the change of magnetic field in space to in time to the change of magnetic field in space, right? Starting from this second equation for the curl of electric field, also taking the curl of it and basically following the same procedure, you will come to the same result for the electric field. So electric field also satisfies this wave equation for the electric and magnetic field. They are essentially the same. Right. So what it means that even in an area without currents or charges, the electric field and magnetic field can propagate in form of a wave. Okay, and on top of that, since these two equations are identical, the relative phase between electric and magnetic field in a propagating wave is zero, right? So they propagate with the same phase velocity, and this phase velocity is written here is just 1 over square root of mu 0 epsilon 0, and is equal to 3 times 10 to the power of 8 meter per second, right? So pretty large velocity for our scale. If you compare this velocity with the distances to other stars, even to our closest star, which is Sun, right? You will see that this this velocity is not that large, not that high actually. Anyway, so another consequence of magnetic field time dependence is the creation of electromagnetic waves, and this result again was derived by Maxwell, and it was a result of introduction of this new displacement current into the equations, which actually helped to satisfy the charge conservation law. Okay, you see this logic. So you would say another way, like without, so you would say that the existence of electromagnetic waves is a result uh, of the charge conservation law predicted by Benjamin Franklin. Very interesting. Let us talk about eddy currents. Eddy current. So eddy current is another consequence of changing magnetic field, and they are induced in any metal. Okay, so if you have any metallic object and you place this metallic object in a time varying magnetic field, this time varying magnetic field, of course, creates curl of electric field, and curl of electric field creates the curl of current, okay, in that metal. And this curl of current, it is what we know as eddy current. Oh yes, this is the schematic picture of this. So you have some coil driven by uh, time varying current. This time varying current creates time varying magnetic field everywhere and around this coil, including the metal. Okay, and this magnetic field creates the curl of the curl of current in this magnetic in this metallic object. This effect can have positive and negative consequences. Okay, positive. I'm aware of just one. Whenever we need to heat something, to melt something, right? For example, this induction cookers, right? Or when we need to melt some metallic objects and so on, it is nice to use this eddy currents effect because other approaches fail, basically. Magnetic fields penetrate in, so suppose you have some big amount of something conducting that you want to melt. Magnetic field just penetrates through this big, large metallic object, right, and creates the currents inside of this object, like heating this object from the inside and from all around its volume. It's much more efficient than just heating, burning some foils and whatever from from one side. Okay. But usually this effect is considered to be negative. So let us discuss a theory of this effect, starting again from the Faraday's law. The changing of magnetic field in this metallic object creates the curl of electric field. The current and electric field connected through the conductivity sigma. The larger conductivity, the larger sigma, which depends, of course, on the concentration of electrons and so on. So substituting this E from this Ohm's law back to the Faraday's law leads to this simple equation, which indicates that changing of magnetic field in time creates the curl of current. as demonstrated here. So this curl of current, this current, right, will be always distributed like a vortex in a metal, winding the magnetic field. On the other hand, neglecting the Maxwell addition and writing this formula for the curl of magnetic field, this form, you can do that always if the change of electric field is not that large. Okay. So taking the curl of this equation leads to this one. Again, rewriting the curl of curl through gradient of divergence minus divergence of gradient leads us to this. Now, again, taking into account that the divergence of any magnetic field is 0, we coming to this equation. And finally, substituting the curl of current from this first equation to this one leads us to this new equation, which is called diffusion equation for the magnetic field. So it has a similar structure to the wave equation, up to one very important difference. The fact that now this equation is first time derivative by time. So this equation doesn't have wave solution. Okay, this equation gets the exponential decaying solution. If we introduce this concept, which is constant, which is called magnetic diffusivity, okay, so basically this constant, this parameter describes how how fast the magnetic field decays in our metallic object. So what actually happens? You have metallic object changing in time magnetic field. This changing in time magnetic field creates the curl of current, and this current dissipates because of the finite sigma. So any metal gets finite conductivity, and this fact leads to conversion of the energy of magnetic field into the heating, right? And this conversion of energy of magnetic field to the heat simply leads to the fact that magnetic field decays into the bulk of the metallic object. And this parameter theta describes this process. We also introduce a new parameter which is called skin depth, which is not just about magnetic field, but well, electric and magnetic field. Okay, so this parameter describes the depth of, well, propagation or penetration of electric and magnetic field inside of the metallic object. Basically this distance from the boundary. Okay, you can see that this skin depth is inversely proportional to the frequency, which means that the higher frequency, the less skin depth, right? And also inversely proportional to the conductivity. So the better metal, which means the higher conductivity, the less the less skin effect. This is, by the way, the reason why we use metals in radio waves and microwaves, for example, for antennas, right? Metals are not that good. They have finite conductivity and they dissipate energy quite efficiently. However, in microwaves, radio waves, the frequency is so high that makes this skin depth skin depth very, very small. So effectively, wave just reflects from any metallic objects without going inside the metal because of this skin depth effect, and doesn't observe much dissipation. Okay, so metallic objects at high frequency don't dissipate energy in scatterings, reflections. For example, antennas, the vast majority of microwave antennas are metallic, exactly for this reason, because they are more efficient because of this very small skin effect. Another example of this effect is a simple mirror. Okay, so how an optical mirror is designed, right? It's basically a dielectric slab, like a glass, covered by the thin layer of argentum, right, the silver. And since the optical frequency, which is hundreds of terahertz, so it's much higher. Because of this high frequency, the skin depth becomes very, very small. In optics, is just around 10 nanometers. Okay, so basically the distance of just a few atomic layers. So in optics, light just reflect from metal, doesn't go too deep inside metal. And this is why this is how any mirror works. Okay, so yeah, the solution of this equation, as I said, is not oscillation solution, is not a wave, but decaying solution, described by this epsilon to the power of minus z over this skin depth factor. Do you have any questions regarding this? Okay. Not only in high frequencies, but also electric grids, for example, right? So any wire, if you calculate, if you simulate using HFSS, for example, ANSYS HFSS, you can do that. If you simulate how the current actually distributed over in the cross section of the wire, you will see that it is more concentrated at by the surface and less concentrated in the middle. So the current is kind of amplified or increased at the surface and reduced in the center because of this eddy currents effect. Okay, you have wire. This shows this a part of this wire. You have this primary current flowing. This primary current, of course, creates magnetic field around this current. And this magnetic field, oscillating in time, creates this magnetic field creates eddy currents, right? And these eddy currents create the secondary magnetic and electric field. So the current is enhanced by the surface of the wire. At the same time, for any current with any finite resistance, we know the formula for the loss power, right? For the power losses, for the power losses in this wire, which is given by this formula, and you of course know that it's proportional to the current squared, which means that in any area where the current is amplified, it leads to quadratic enhancement of the losses. Okay, so this is why this effect is so important, and sometimes we need to or want to get rid of this effect, mitigate this effect, and one solution to this effect is to make the wires not just hold wire, sorry, wall wire, but make it from a number of wires with with a smaller diameter, to ensure that the current distribution across every single wire in this in this total wire is homogeneous. Okay, so pretty much the how's it the this electric engineering of electric grids of energy transfer is about how to reduce the negative effect from this skin effect and so on. So those people very how's it very much against, they don't like when current is increased in any area, because this increasing of current means reduction of total efficiency. Yeah, this is called leads wire. Yeah, and about transformers. So transformer is what? Transformer is something that allows to transform or change electric voltage from one level to to another level, right? If you reduce the voltage, it is stepping down. If you increase the voltage, it's stepping up. This is how this system looks like typically, right? You can see this this core made of ferromagnetic. Okay, so ferromagnetic is a material with very large magnetic permeability, right? So basically the reason why we need this ferromagnetic material, because it concentrates magnetic field inside of this metallic core without spreading magnetic field much around. So the magnetic field will be concentrated in this core, and in the perfect ideal case, the flux from that goes through one coil will be equal to the flux to the second coil. Yeah, this is the schematic picture of any transformer. You have one primary winding, one primary coil, the secondary coil, and this magnetic flux induced in the core. The transformers can be of different design, different geometry, can contain different number of windings and so on. This is an example of the transformer that you will be asked to simulate in your next lab work. Okay, so this is lab work design. So transformer includes at least two coils. Okay, primary and secondary, and writing the this electromotive force, this induction formulas for the first and second coil in this way, right, through the flux. And as I said, the flux in the ideal perfect case for the perfect transformer, the flux through first and second coil are the same because they are sitting on the same core. And since the flux is the same, their time derivatives also the same. So I can write, I mean, the time changing in time of the fluxes are equal, which leads us to this simple formula that basically dividing the EMF in the second coil by EMF in the first one, we got this simple formula that connects links the EMF change in the transformer to the winding number difference, right, in the first and second coil. This is for electromotive force. Of course, in the case of perfect transformer, if we have no or if resistance of these windings are neglected, right, we can write the same equation not through EMF but through voltages. Okay, so this way we get this more kind of well-known formula of a transformer. So the ratio of voltages is equal to the ratio of winding numbers in the prime and second coil. And let us, as an example, take a case when the winding number in the second coil is 1000 of winding number in the first coil, right? Doing this, we will come to the conclusion that this transformer will raise the voltage by a factor of 1000. Okay, so let's say if in my primary coil I apply maybe just 1 voltage, in the output in the second coil I will get 1000 volts. So one can say, is it safe, right, to work with this 1000 volts? For example, on internet you can find different designs of devices that step up voltages from, for example, a simple battery 1.5 volts, which is of course completely safe, right, safe device. So you can raise this 1.5 volts up to 1000 volts, for example. So in the output you will get 1000 volts. And yeah, so is it that dangerous? Of course, the answer is not really, right? Because voltage is meaningless without stating the power, right? So what is the primary thing is the energy, is the power. Power is what we transfer through the electric grids. Power is what we consume. Power is the main thing. The voltage is just secondary. The voltage is nothing without stating what is the current in the circuit, right? So the fact that we raised voltage by a factor of 1000 means that we reduce the maximum current in that circuit also by a factor of 1,000. And in order to exemplify this, let us state that, for example, in the ideal, in the perfect transformer, the power in the first coil must be equal to the power to the second coil, right? Which leads us to this simple formula. And finally, to this one. So the ratio of currents is kind of reversed, right? Comparing to the ratio of the voltages. So if you increased the voltage by a factor of 1,000, you reduced the current also by a factor of 1,000. In a perfect case, in a real case, of course, this will be even less. So such a device is completely safe. Let us say a few words about the use of transformers, right? Of course, we use transformers basically every day. Anytime we need to step down the voltage from 120 in our outlets to the whatever voltage is consumed by our electronic devices, right? Typically, it's about 3, 5, 12 volts. We use transformers in electric grids, right? So how a typical electric grid is arranged? So typically we have some sort of a generator. This generator can have several phases. It doesn't matter here. What matters is that these generators generate the voltage at the level of around 10 kilovolts, which is considered to be quite weak, quite small voltage, low voltage. Then we use transformers to step up this voltage to a much higher levels, to let's say 400 kilovolts. I heard that FPL lines here in Florida, they work at 500 kilovolts, so very high voltage. And then we transfer this energy, these voltages, closer to the customers, right? First we step down these voltages to, again, something around 10 kilovolts using one high power transformers, and then using smaller transformers we step down the voltages to the customer level 120 volts. So the question is why, right? Why we need to raise this voltage from 100 volts up to hundreds of kilovolts? Why we need to arrange all these electronic grid lines in in such a way? So obviously it's very expensive to to line all these wires so high from the ground and transfer these hundreds of kilovolts. So obviously it's not cheap, right? So why we do that? Of course, some of you know that the answer is because it is more cost efficient. It's more effective way. Why? Because again, what we actually deliver to the customers is power, right? The power which is consumed by customers, by people, whatever the commercial use also, is the product of voltage per current. Okay, product of voltage and current. This is the power we deliver, we transfer. However, these wires are not free of dissipation, right? They have finite resistance, and this finite resistance leads to power dissipation, and this power dissipation is described by this power loss formula, and here the current is to the power of 2. Okay, so it's a exponential factor. If you increase the current by a factor of 2, right, the consumed power is increased by the same factor, by 2, but the loss power is increased by a factor of 4. So increasing current means you lose for the heating. So the way to make these lines more efficient is to reduce the current in the wires, okay, using transformers. So, and it inevitably leads to increase in voltage, in proportional increase in voltage. And if you calculate all these numbers very carefully, even taking into account the fact that you need several transformers, right? In this simple case, you have 1 transformer, 2, 3. So you need 3 transformers. You need all these high level, high attitude lines, and and so on. So still, all these factors will be cheaper than and more efficient than just transferring electricity at the low voltage level. Yeah, so reduced currents lead to exponentially lower losses, enhancing transmission efficiency. Do you have any questions so far? All right. And I guess, yeah, so this is basically it. So next week, you supposed to do this lab 3, numerically simulate an electric transformer. I will make this assignment very soon, hopefully tomorrow. So this is basically it. Thank you very much. Let me stop the recording.